Hello, this is the third video of lecture 6. I'm going to talk about shadow prices. What are they? The optimal value of dual variables are shadow prices. The shadow price associated with a particular constraint tells you how much you would be willing to pay for an additional resource. What is the value of 1 unit for your resources? How much more profit you would get by increasing the amount of that resource. But how we can find shadow prices? One way is solving the dual problem. So you have the primal problem, formulate the dual problem, and solve the dual problem. Assume that your shadow prices are y1 0, y2 3, y3 1. If the profit of the unit of profit is dollars, it means that by increasing 1 unit of second resource, you will earn $3. You will earn more $3 in terms of profit. By increasing 1 unit of resource 3, you can make $1 more. By increasing 1 unit of resource 1, you don't make any money because you already have resource 1 available. You haven't finished resource 1, so by increasing that resource 1, there is no more money. You cannot make more money. Shadow prices are optimal point or optimal solution of the dual problem. So formulate the dual problem, solve it, you will find shadow prices. Another way is find the value of shadow prices from the optimal table of the primal problem. You already solved the primal problem through simplex algorithm. You have the final table of the optimal of the primal problem, and from that final table you can find the shadow prices. Let's see how. Assume that your final table of the primal problem is this. x1, x2, s1, s2, r1, r3. So we have artificial variables for some constraints. Basic variables are x1, x2, s1. Since we have 3 basic variables, we will have 3 dual variables in the dual problem. I don't care about the numbers here. The only numbers are important are in the objective function row. It is 1, 0, 0, 0, 3, m, 1 plus m, 36. When you want to find the shadow prices or optimal solution to the dual problem, you need to look at the objective function row in the final table of the primal problem. You have S1 and you have R1. So this constraint was a greater than or equal to constraints. You had minus S1 plus R1 on the left side of this constraint. Whenever you have artificial variable for a constraint, you just need to look at the coefficients of artificial variable, which is m here. So for finding y1 value, shadow price for first resource, you need to look at this coefficient, which is 0 plus m. I intentionally added to the 0 because I want to show you how you calculate or estimate y1. For y2, we just have s2. There is no r2. It was a less than or equal to constraints. So this coefficient is 3. For y3, we have just r3, artificial variable, 1 plus m. It's a maximization problem because here we have positive 1. Since it's maximization problem, you don't need to multiply the result by negative 1. So you just need to remove m wherever you have it, and you have your shadow prices. That's it. So from the final table of the primal problem, you could find the optimal solution of the dual problem. Let's have another example. y1, y2, y prime 3, y double prime 3, s1, s2, r1, r2. 6, 0, 0, 0, 2, 6, minus 2 plus m, minus 6 plus m, 36. Okay, we have two basic variables in this problem. The dual of this problem will have two decision variables. So since it is y here, I'm going to call them x1 and x2. For x1, you look at, since we have r1, you look at the coefficients of artificial variable for constraint 1, negative 2 plus m. Again, we have r2 and s2, so the coefficient of artificial variable in the objective function rho 0, negative 6 plus m. You just need to remove m, multiply it by negative 1 because it was a minimization problem. The primal was minimization problem, so you need to multiply it by negative 1. x1 is 2, x2 is 6, and that's it. This is the optimal solution of the dual of this problem. There is also a relationship between primal and dual, and it's about the corner points. Because the dual problem is a linear programming problem, it also has some corner point solution. The augmented form of the dual problem, it means that after adding slack variables and make the constraints to be equal, the augmented form has n plus m variable. So what do you remember that we had a formula to calculate the number of corner points? It was n plus m factorial over n factorial m factorial. In the primal problem, we have n variables, m constraints. In the dual problem, we have n constraints, m variables. So the result of the number of corner points for both problems are the same. The number of corner points in the primal problem is equal to the number of corner points in the dual problem. It means that for any corner point in the primal problem, there is a corresponding corner point in the dual problem. The primal is maximization of CTX, C transpose X, AX less than or equal to B, X greater than or equal to 0. I can write this in an augmented form, CTX AX plus S slack variables equals to B, X and S greater than or equal to 0. The dual of this is minimization of right hand side values, B transpose Y, A transpose Y greater than or equal to C, Y greater than or equal to 0. The augmented form of the dual problem is bty aty minus some slack variables. I'm going to call it t to distinguish between s and t. It's greater than or equal to, so it's minus t equals to c. Y and t are greater than or equal to 0. There is a complementary slackness relationship between these two problems, and it's this: the multiplication of x and t equals to 0, the multiplication of s and y equals to 0. For every variable here, for every x here, we have one constraint, and for any constraint we have a t. So the value of x multiplied by the value of t corresponding to that variable is equal to 0. For any constraint here, we have a variable here. So the value of s for constraint 1, for example, multiplied by y1 equals to 0. This is complementary slackness relationship. Let's have an example to use this xt equals to 0 and sy equals to 0. The primal problem is maximization of 8x1, 4x2, x1 plus x2 less than or equal to 10, 5x1 plus x2 less than or equal to 15, x1, x2 greater than or equal to 0. If you draw this problem, you will get 10, 10 for the first constraint. The second constraint will be 15 here, 3 here. This is the feasible region. We have 4 feasible corner points. Totally, how many corner points do we have here? N is 2, number of variables. M is 2, number of constraints. So from the formula of n plus m factorial, n factorial, m factorial, it's 4 factorial, 2 factorial, 2 factorial. It's 6. Totally, I have 6 corner points, feasible and infeasible. 4 of them are feasible, plus these 2, 6 corner points. The dual of this problem is minimization of 10, 15. 10 y1 plus 15 y2. y1 plus 5 y2, 8 for the right hand side. 1 y1 plus 1 y2, 4. Both variables are greater than or equal to 0, so we need natural constraints for minimization problem. Both are natural here, so both of them will be non-negative variables. Let's draw the graph of this problem as well. The first constraint, y1 is 8, y2 is 1.6, 8 divided by 5, 1.6. This is 8, this is 1.6. Second constraint, both of them are 4. Greater than or equal to 0, so this is the feasible region. We have 3 feasible corner points. Again, n plus m factorial, n factorial, n factorial, you will have 6 corner points in you have 6 corner points in the dual problem. 1, 2, 3, 4, 5, 6. All of them are 6, but 3 feasible corner points. We have this relationship between xt and s and y. So I'm going to have this relationship in the example to show you how it works. Let's assume that I'm looking for this point. Let's call it A. x1 is 3, x2 is 0 at this point. I would like to find the corresponding corner points related to this A in the dual problem. Which one of these corner points correspond to A? 6 corner points, 6 corner points. So for each of them, here we have a corner point there. x1 is 3, x2 is 0 here. What about s1 and s2? x1 plus x2 plus s1 equals to 10. Since x1 is 3, 3 plus 0 plus what will be 10. which is 7. So S1 is 7. What about the slack variable of second constraint? 5 multiplied by 3 plus 0 is 15. 15 plus 0 is 15. So S2 is 0. We have this point as an A in the primal problem. Let's find the corresponding corner points to A in the dual problem. Since xs, this is our complementary slackness relationship, xs equals to 0, t equals to 0, just as a reminder. Since x1 is 3, we have the relationship of xs equals to 0. It's something positive. So I can conclude that x1 is 3, s1 definitely is 0, because the multiplication should be 0. Here also s1 is 7, so the corresponding variable to this s1 is y1. S should be 0. I'm sorry, this is xt, this is ys. So since x1 is, I confused s and t here. If x1 is 3, since xt is 0, x1 is 3 is a positive value, t1 should be 0. Since s1 is a positive value, because of this formula, y multiplied by s equals to 0, y definitely is 0. y1 is 0. So here, in the system of equation of the dual problem, I know that t1 is 0, y1 is 0. So let's just plug in these values in the first constraint. y1 is 0, also t1 is 0. 0 plus 5y2 minus 0, because t1 is 0, minus 0 equals to 8. 0 plus 5y2 minus t1, which is 0, equals to 8. So what is y2? 8 over 5, which is 1.6. So I can write that y2 is 1.6. Let's see what is t2 in the second constraint. I know that y1 is 0 plus y2 is 1.6 minus t2 is 4. y1 plus y2 minus t2 equals to 4. What is t2? It's 1.6 minus 4, which is negative 2.4. So t2 is negative 2.4. What point here is A in the dual problem? 0 and 1.6. So this is A. As you see, it's an infeasible corner point. So you can find all of the corresponding corner points of all of these corner points in the primal problem. For example, A is A here. If this is C, if you solve the problem and find the corner point, is gonna be this one, C. This is B, this is B, and so on. There is an exercise in slide 33. Solve the following problem by graphical method. The exercise is this: minimization of 2x1, 3x2, 5x3, 2x4, 3x5, x1 plus x2, 2x3, x4, 3x5 greater than or equal to 4. 2x1 minus 2x2 plus 3x3, x4, and x5 greater than or equal to 3. All variables are greater than or equal to 0. The problem asked us to solve this one from with graphical method. We have 5 decision variables, so it's impossible to solve the problem through graphical method. What can we do here? As you see, we have 2 constraints. It means that the dual of this problem will have 2 variables. If we formulate the dual with 2 variables, then we can solve the dual problem through graphical method and find the optimal solution of the dual. From the optimal solution of the dual and this relationship, we can find the optimal solution of the primal problem. So let's do it. The dual of this problem is a maximization problem. 2 constraints. I'm going to have 2 variables. 4y1, 3y2. Since we have 5 variables in the primal problem, I'm going to have 5 constraints in the dual problem. The first column will be the coefficients of the first constraint in the dual. y1 plus 2y2. 1, negative 2. 2, 3. One plus 1. 3 plus 1. Right hand sides will be the coefficients of the objective function. 2, 3, 5, 2, 3. Since all of the variables are non-negative, we are going to have natural constraints for maximization problem, which is less than or equal to for all of them. Minimization problem, both are natural. So y1 and y2 both are non-negative variables. Let's draw the graph of this problem. y1 plus 2y2 equals to 2. y1 minus 2y2 equals to 3. We have 5 constraints here. I don't want to spend time on finding the solution of the graph because I already had a lot of examples of solving the problem through graphical methods. So I'm just gonna check the optimal solution of this problem. After solving it through the graphical method, it's 0.8 for y1 and 0.6 for y2. Okay, through graphical method we could find y1 and y2. From y1 and y2 you can find t1, t2, t3, t4 and t5. You don't need to calculate all of those t's, you just need to check that which one of them are positive values, which one of them are 0. So let's check them. 0.8 plus 1.2. 0.8 plus 2 multiplied by 0.6 is 2. So t1 is 0. What about t2? 0.8 plus minus 1.2. So t2 is not 0, it's something greater than 0. I don't care how much, what is the value, but it's not 0. t3, again, it's a positive value. t4, a positive value. What about t5? 3y1 plus y2 minus t5 equals to 3. It's 0. Okay. From t2, t3, t4 greater than 0, I can say that x1 is 0. Excuse me, x2. x3 is 0. x4 is 0 because the multiplication of them should be 0. t2, x2, 0. t3, x3, 0, and so on. So I already know that in the optimal solution of this problem, x2, 3, and 4 will be 0. Also, from y1 and y2, which are not 0, I can conclude that s1 is 0, s2 is 0. s1 multiplied by y1 should be 0. s2 multiplied by y2 should be 0. So you just need to plug in all of these zeros in these two constraints equations to find x1 and x5. So let's do it. x1 plus 0 plus 0 plus 0 plus 3x5 minus 0 equals to 4. 2x1 plus 0 0 0 x5 minus 0 equals to 3. So this is the system of equation. You have x1, x5, two unknown variables, two constraints. You can find x1 and x5. After solving that, x1 will be 1, x5 will be 1. So your optimal solution of the primal problem through graphical method, you didn't need to solve it through simplex algorithm, is 1 0 0 0 1.